Okay, yeah, we just talked about how this was the area of a trapezoid, and this is the formula for a trapezoid. All right, let's see if we can go on. What if? Ooh, awesome. So is this, can we use a trapezoid? Because it's not a straight line, it's curved. If I can get this to work, go. Okay, we could split into a lot of thin trapezoids, and that would give us an estimate. There we go. So it's a little bit better than rectangles, right? They are. They are tiny little. You can see, like, if you zoom in right here, you can see a little bit of where it's not actually fitting. You can see a little bit right here, right? It seems reasonable. Yes, it does seem reasonable. Okay, so up here, right, we've got this function. What's this thing? The antiderivative. Well, right now, we're just going to say it's an antiderivative. The integral is like, we're focusing on the definite integral. So remember, we're just focusing on from 0 to 4. So this is going to be used to find it. Now it's also missing what at the end? Plus c. That's right. So we talked about just a second ago, this involves the assumption that um, the velocity, well, let's see, it's the position, not the velocity, that the position is 0 at time 0. That's kind of an assumption that we're doing. And why is this a 3? 1 higher than 2. And then this is 24. Where did they get that? Yeah, 3 times 8. So we wanted to think about if this were a 3, right, what number, if I divided 3 into it, would give me this 8, and that's this 24. So working backwards, and then this 1 becomes the t. And if this were a plus 2, this would become 2t, right? Oh my. Okay, we're back. We just lost one. So where did the t's go right here? They turned into 4s. They did, right? Because we're trying to integrate it from 0 to 4. Okay. And then that's just we're calculating, right? So this is our area under the curve. Now, is this an approximate value or an exact value? It is exact because we used the antiderivative. We didn't use the trapezoids, right? Okay. We can use the antiderivatives to find the area under the curve. That's correct. Oh boy. Now this part is a little tricky to follow. Are you ready? Okay. Love it. Okay, so here's what's going on. This weird notation, a sub a of x is the area under the curve from the first point will be a to the next point will be x. A is going to be a constant, x is going to be a variable. So here's our picture from a to x. So what we're doing now is we're going to look at two parts, and we're going to try and build up an expression that will relate. Why is it that the antiderivative tells us the integral? Because we've just kind of shown that it happens to be true. Here we're going to kind of analytically demonstrate that it must be that way. See the difference? Okay, we're going to try and explain it. So here's a to x, which is this first little term. It's from a to x. That's our expression. This one's going from x to x plus h. So the a is now sub x, and it's going to x plus h. If I want the entire area down here, it would be the area from a to x plus h. So that left side all makes sense? Are you sure? What number do I put as a subscript when I'm... All right, so the starting value would go here. Yes. And what goes in the parentheses? The ending value. And the A stands for the area, right? Okay, so On the right, we have an equation just describing that if I add these two together, if you look at the green and the unshaded region, if I add those, I should get the area over here on the right. Is that all? Okay. So this is just a slight rearrangement where I've taken the right side to the left and, excuse me, I haven't done that. I've actually subtracted. So this area from x to x plus h, this part right here, the unshaded, I've left on the left side, and I've subtracted the green region to the other side. So area from a to x plus h minus the area of a to x. So it's saying the whole thing minus the green is going to give us this white unshaded region. Now, does this remind you of anything? Parentheses x plus h minus parentheses x? The form, yeah, the definition of the derivative, okay? So that's going to be where we're headed. So think about the two rectangles. You've got a minimum rectangle that is going to be less than the actual area under the curve. You've also got a maximum rectangle, right? That's just always going to be a little bit more than the area in the curve. These are approximations, okay? So think about the actual area has to be between those two. Kind of like thinking back to like the squeeze method, we're kind of in between those. All right, and here we're saying that if I multiply h by the height of the minimum rectangle, that's my small estimate area, h by the maximum height over here is the larger bound, and then the actual area is somewhere between there. See that? So it's area, smallest area, largest area, and then this is the actual area, is somewhere between those values. Now notice what happens if I want to solve for the minimum value of f and the maximum value of f. I would do what to all three parts? I would divide by h. And this may look even more familiar. You see that? I know. Okay, we need to wrap this clip up. It's getting long. So the minimum value of f and the maximum value of f are the boundaries for this. Now, as h gets smaller and smaller, these two approach one another. Does that make sense? The minimum and maximum get closer together. So as our h is approaching 0. Now, the limit, the farthest it could reach, right? If you carry that on forever as you approach closer and closer to 0, the limit would be the actual area, the perfect area, because these two would kind of squeeze that area in between them. And now that fits perfectly. We have a limit as h approaches 0 of a sub a to x plus h minus a sub a of x over h. So that is our definition of the derivative. So this is what we have. So the derivative of the area function is this f of x over here. Come on, you can do it. There we go. If we take the antiderivative of both sides to find a formula for how we would get the area, I gotta keep moving this thing around. We get, right, the derivative of this over here. Dun, 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 dun. Oh, sorry, I messed that up. We're not taking the derivative. What are we doing from here to here? Antiderivative, right? So this is the derivative of capital A. If we do the antiderivative, it just gives us capital A. So we're working backwards. We're undoing the derivative. So that's the notation. If you have a function, lowercase f, its antiderivative is denoted with a capital F, meaning that the little f comes from, where's the derivative of capital F? A double integral? We're going to do double integrals at some point. Let's just wait. Let's just wait. But for example, yes, if we start with acceleration, the integral of that's going to be velocity, and the double integral of acceleration is going to be our position. Let's just wait and hold on to that question for right now. I'm trying, so the plus c, we need to sort that out really quickly. So the initial value from a to a is equal to f of a plus c. Now the initial area, if you're going from that constant just to itself, there's not going to be any area. So that's why this is a 0. So if I do a quick subtraction, c, the constant, is the negative integral of just a. Okay, so substituting one more time back up here, the area of that region is the integral at x minus the integral at a. So this was the ending value, this was the starting value. Oh man. So the area under the curve from a to x is the antiderivative of x, the last number, minus the antiderivative at a.